Hi, my name is Sylvia Oivari, and I'll be presenting my project for deep learning at Harvard Extension School. And this project is on predicting robotic grasp quality. So this grasping data set was obtained from a simulation in Smart Grasping Sandbox. And in the simulation, we have a robotic arm picking up this red ball you see here. And the robotic arm picks up the ball in different configurations. And then what it does is it shakes it. And how we're deciding the quality of the grasp is called the robustness, which is measured by the variation of the distance from the palm of the robot to the ball. So if the ball is grasped really tightly, the variation would be really small when it's shaken. If it's grasped kind of loosely, I would imagine that it ends up shaking a bit more inside the palm. And if everything fails, the ball just ends up on this table, I believe. I don't know if it can end up on the floor. And so that variation would be really large, and the robustness would be large. So small robustnesses are good. And this particular data set is available on Kaggle, and it's about 500 megabytes. There's definitely much larger, more interesting data sets for this type of problem available online, where it's multiple robots in real life grasping a variety of objects, and you get images of those objects and many, many more variables. But those are much larger data sets, and when I tried to work with one of them, my computer memory ran out, so I ended up working with this really nice data set anyway. Okay, so the variables that we're looking at while this grasping is happening is the position of the joints, the velocity of the joints, and the effort measurement of the joints. So the columns are labeled according to hands, fingers, and joints. So in this data set, there's only one hand. We're doing the grasping. But this hand has 3 fingers, and it also has 3 joints it can use. So from this, we get 3 times 3 times 3 variables. So that's 18 total numbers we can look at each time point. And how the experiment works is there's a total of 30 time points potentially for each experiment. Sometimes it's cut short for whatever reason. So the hardware used for this project is a Lenovo T470 ThinkPad laptop with an i5 CPU processor and 16 gigabytes of RAM. Unfortunately, there's no GPU involved here, so things can get a little slow. Software used is Windows, and I wrote the code in Jupyter Notebook. And the libraries used are Keras for implementing the deep learning, Pandas and scikit-learn for cleaning the data. And the models used in this project are a fully connected model, LSTM models, and a bidirectional LSTM model. So the first thing I did when I got this data set was plot a histogram of the robustness. So on the y-axis is the counts of the robustness, on the x it's just the robustness value measured. So you can see that there's really 2 peaks, one between 0 and 25, and then this larger one between 75 to 150. So my interpretation of this would probably be, if I was just looking at this, that this peak is where the robustness is low the variation of the ball shaking is low, and so the robot is holding onto the ball, and probably this peak is where we have let go of the ball and it's just charting its own path somewhere. So the data curator recommended that 100 be the threshold point between where the robot is holding the ball and the robot is dropping the ball, which doesn't completely make sense to me. It seems to me that 50 would make a better threshold point. But I assume he knows what he's doing, so we ended up using 100 for the threshold point throughout the experiments. I actually did end up trying to use 50, and what happens is the accuracies of the models actually goes up like crazy. I get 99% accuracy. I'm still not sure why. But anyway, we're using 100 for the threshold. So previous work on this data set that I saw was a single layer LSTM model, which takes into account the time aspect of this data, as well as a fully connected model. So the way I expand upon this is to include a double layer LSTM, as well as a bidirectional LSTM model. And in previous work, these models were only used to predict a binary value of whether the grip is good or not good, and I decided that we'll try also predicting the actual robustness value. So for the binary classification problem, I used a binary cross entropy loss function with an atom optimizer. And for the regression model, I ended up using a mean absolute error loss function with an atom optimizer for all the regression problems. And all these models are trained for 50 epochs with batches of 100. And on my CPU machine, each epoch takes about 1 minute. So generally the models take about 50 minutes to train. So this is how I set up my models in code for the fully connected binary model. I have first a dense layer with 18 units. My input shape is 30 by 18 because there's 30 time points in each experiment, and then there's 18 variables that we're measuring. And a ReLU activation is used. I then do a dropout of 0.2, and finally I flatten it so it will go into this final single dense layer with a sigmoid activation to get that binary prediction. And finally, I compile with a binary cross entropy loss and an atom optimizer. For the fully connected regression model, basically everything is the same except what I'm doing with the final layer is the activation is linear, is the automatic activation if you don't put anything on this line. And then I compile it with an MAE loss function and an atom optimizer. So for single LSTM, a binary prediction, we're using, in this case, the units are 128. The input shape is again 18 by 30. The dropout number and recurrent dropout are both set to 0.2 in this case. And the activation is sigmoid, so we get our binary results. And similar things are happening in the regression model, except again, the dense layer is linearly activated. So I thought it might be interesting to try using a double layer LSTM in case that would improve the prediction. So same thing as before, except we add a second LSTM layer. And finally, I tried using a bidirectional model. And how you do this is you just do .add bidirectional and you put in your LSTM layer as an argument. So it's the same LSTM layer as before. We do our sigmoid activation, we get our binary results. And again, we do this for a regression model. So the results for the binary classification, basically look like this is a function of epoch, where the y-axis is validation loss. So you can see that the fully connected layer takes a fair bit of time to catch up with the other ones. And maybe the bidirectional layer has a bit of a head start on the other ones, but at the end of the day, they're all having similar validation losses. And this is definitely mirrored in the validation accuracy, where basically they all end up at about 0.88 accuracy. So 88% of the time we are correctly predicting if the robot is dropping the ball or holding the ball. So in the regression results, again, the fully connected layer is taking a lot longer to converge, and it never actually ends up converging on this value of 7.5 that the other ones get to. So for whatever reason, when we're actually predicting regression, the fully connected layer is not happy with that. Excuse me. So again, we actually see that the bidirectional model has a bit of a head start on the other ones, but at the end of the day, they all have similar losses. So the final validation loss for the fully connected layer is 10, while all the others are about 7.5. And the validation accuracy, unsurprisingly for the fully connected model, is only 0.84. And for all the other models, it's 0.88, which is very similar to what it was previously, except previously the fully connected model actually did a much better job of predicting if the ball was going to drop. So because the bidirectional model performs slightly better, maybe this indicates that both the present and future states of the robot are important for grasping objects. So here are my references with the Shadow Robot dataset. Shadow Robot is the company where the guy was working at, and this is available online. And these are the code that I ended up editing a little bit and starting from. Thank you. Okay.